All right. Sorry, I lost it. Okay, there it is. Hey, all right. Hey, everybody. Sorry, I just started pushing record. So welcome back to lesson number 2. It looks like, yes, we can all see the vector addition tab on my browser. So that's good. I just wanted to take a quick moment and pop on over to our class webpage so you know exactly what you're looking at. Hopefully you guys have seen or logged into Canvas before. So you should have seen something that looks like this probably. Your view might be a little bit different than mine because I'm the instructor, so I might have a different view than you. But here's our class right here. So I'm going to click on our class. I did change the welcome page last night to reflect my love of cat memes. So there it is for you. And then yesterday, after our class, it did take a little while to compile the video, but here it is on the homepage, a link to the YouTube channel where I'll be posting all of our Zoom lesson videos. So you can just click that link. It'll take you there to this page, and ta-da! There's our first session right there for you. So I'll be updating that every day, but this link will always stay the same. That'll take you right to my channel. So you can just click whichever video you need to see. As far as the question of how do you find the pretest? Well, there are a couple of different ways that you can do it. You can come over here to assignments, and it's right now the only assignment that's in there for you. Or you could click down here in quizzes and it will show you the same thing. Okay, but you click your physics pretest, and then I guess for you, it would launch you into the test. Okay. Any questions about those two things? Nope. All right. Feeling good. Great. Great, great. Okay. So let's come back over here then to our PowerPoint. This is where we stopped yesterday after our topic of units and conversions. Can you guys all see the PowerPoint? Getting some no's. Okay. How's that? All right, technical difficulties. Give me just a second. You're still seeing Canvas. Okay. Better? Fingers crossed. Yay! All right, great. We're rolling. Thanks for your patience again. I'm new to this whole teaching over Zoom. So here we go. This is where we left off yesterday with units and conversions, and I gave you that bonus problem about the asteroid. So how many of you attempted the problem? And if you feel comfortable, send me your answer. You can send it to me privately too if you don't want to send it to the entire class. You tried and it made you mad, so you stopped. Attempted and failed. All right, totally fine. I'm glad you tried. Okay, good. Got some answers. Good, good. Yeah, this problem was a challenge problem. That's why it was a bonus problem. It was supposed to challenge you. Oh, I'm so sorry about that. Difficult to see the question with tears in your eyes. Okay, well, I'm going to show you the answer, but I'll also kind of verbally walk you through the problem. I didn't write it out step by step in the PowerPoint, but I'll go ahead and do that before I post this PowerPoint onto Canvas. All right, so here is our bonus problem about the asteroid, which has a radius of 3.5 kilometers, and we had to figure out how what the mass of it was in terms of cruise ships. And the answer is 2,690,000 cruise ships. So it looks like a lot of you, or at least those of you who are posting your answers, got the correct digits, which is a good start. So here's how we needed to kind of go about doing that. I can hold up my work. That's probably backwards, so sorry. So I'll just walk you through it. So what we're given, if we identify our variables, what we're given is 3.5 kilometers as the radius. We're given the density of the asteroid, which is 3,000 kilograms per cubic meter. And we're given that the asteroid is a sphere. So of course, that's a totally idealized case. Asteroids are not actually spheres. They're not massive enough to be spheres, but just for the sake of simple math, that's what we're assuming. So if you remember from things like chemistry, maybe physics, if you took it, the volume of a sphere is 4/3 pi r cubed. And the density of of anything is mass over volume. So if we're given the density and we need to find the mass, and we know density is mass over volume, that means we need to find the volume too. So once we plug the radius into our volume formula, I'll type that into the chat so that you can all keep that in your mind. Volume is 4/3 times pi r cubed. Oh, sorry, that was the wrong place. Everyone. Volume equals 4/3 times pi times r cubed. That's our volume of the sphere. So we plug our radius into that, and that will give us, the volume of our asteroid. So if the density is mass over volume, that means that mass is density times volume. Right? That's one of those algebra skills that I want you to be comfortable with, is taking an equation and rearranging it to solve for the variable that you need. Okay. So our density then we have right there, the units are kilograms per cubic meter, but unfortunately our volume units are now in cubic kilometers. So we need to convert cubic kilometers to cubic meters before we can plug that in there. Okay. And that gives you an answer of 5.39 times 10 to the 14 kilograms. But the answer that we want is not in the units of kilograms, it's in terms of cruise ships. So we need to take that answer that we got in kilograms and set up our ratios like we had talked about yesterday. So since we have kilograms on the top of our first ratio, we want kilograms in the bottom of our second. So we have 1 metric ton over 1,000 kilograms times our second ratio is 1 cruise ship over 200,000 tons. And that way kilograms will cancel out, tons will cancel out, and we're left with just the unit of cruise ships. So our final answer is over 2 million cruise ships. That's crazy. Like, just think about that for a second. Like, it blows my mind. Okay, so we take this asteroid that's a radius of 3.5 kilometers. That's like not a very far distance. And it has a mass of more than 2 million cruise ships. Like, I just can't even, space blows my mind. So that's super, in my mind, super cool. Okay. So today's topic is vectors. I don't know if any of you are Despicable Me fans, but I love this movie when it came out. And I show this clip to my students every year when I teach vectors because it's just so memorable. So for those of you who don't know, Despicable Me is a movie about a villain who tries to steal the moon. And he meets this other like rival villain named Vector. So there you can see a clip of them meeting. And Vector says he commits crime with both direction and magnitude. And it just gets me. I love it. So this is sections 1.7 to 1.10 in the textbook, but really today we're going to focus on 1.7 and 1.8. Vector spans. Okay, and this topic is actually pretty important because most of the topics, most of the units that we'll go through in physics deal with vectors. Things like forces, acceleration, velocity, momentum, all of these things deal with vectors. So I want to make sure that we have a pretty good understanding of them. All right, here we go. So there are two different types of quantities that exist in the world. One is a scalar quantity. So a scalar quantity is something that just has a size, just a magnitude, and not a direction associated with it. So for example, that would be things like time, mass, dollars, and distance. When we think about directions, we think in terms of like north, south, east, west, or forwards and backwards, up, down, left, right, things like that. So you can kind of think about like, yeah, going forward in time, going back in time, but you can't go like left and right in time. That doesn't really make sense. You can't go north in time. So that's why it's a scalar quantity. Mass, you don't have to be like 4 kilograms north. That the direction just does not matter for scalar quantities. Do you guys know of any other quantities that are scalar? So where the size is the only thing that matters and we don't associate it with a direction. If you have them in mind, type it in the chat. Let me see what you think. Numbers, true. Yeah, there's no direction associated with numbers. Volume, good. Speed, yep, absolutely. Temperature, yes, good. Mass, yep. Acceleration is a little bit tricky. The direction does actually matter for acceleration, and we'll go through, I think, tomorrow why the direction matters for that one. Current, that's an interesting one. Wavelength, good thought. Yeah. I like it. You guys are coming up with some that I like didn't even have in my notes. So that's great. Good thinking. Energy also is one where the direction doesn't particularly matter. Density, power, yeah, great. So when we're dealing with scalar quantities, the math is pretty simple. It uses really familiar algebra. So you can see there I have a couple of examples. 6 kilograms plus 3 kilograms equals 9 kilograms. Simple, right? 4 times 2 seconds is 8 seconds. Easy enough. Easy peasy. Okay. The other type of quantity that exists in the world are vectors. So we have scalars where the size matters, scalars, size. Vectors, like our great supervillain, they are quantities that have a magnitude, a size, and a direction associated with them. So those are things like displacement, velocity, acceleration, force. With these types of things, it matters which direction that particular thing is going in. So in the previous slide, I had distance as a scalar. Miami is 300 kilometers away. But displacement would tell us Miami is 300 kilometers south. That just gives us a little bit more information about that particular distance, but that displacement associates a direction with it. Okay, velocity tells you how fast you're going in a particular direction. Speed just tells you how fast you're going, right? When you get pulled over by the cops for speeding, they don't care what direction you're going. They just care how fast you're going. Okay, so speed is just size. Velocity is a vector. It tells you how fast you're going in a certain direction. Okay, force. It matters if I push my computer this way off the stool versus to the side versus towards me versus down. Those will all have different results. And so the direction of my force makes a difference. Force is a vector. So when we're dealing with vector quantities, we represent them as arrows because an arrow has a definite length and that arrowhead is pointing in a specific direction. So it's perfect to represent a vector that has a size and a direction. So we represent them with arrows, and the angles that we measure for the direction are always measured counterclockwise from the positive x-axis. That's just for the sake of convenience and not complicating things. So whenever we talk about angles, they'll always be measured counterclockwise from positive x-axis. So the symbol there, I just wrote a generic vector. If we're talking about vector A, for example, you would see it written in bold with a little arrow symbol over top. Like if you're looking in a textbook, that's how they would show a vector quantity as opposed to a scalar quantity. The magnitude would be just the letter by itself, not bold, not little arrow on top. And that's what we would see for a scalar. Because remember, for a scalar, the size matters, the magnitude matters, not the direction. Another way to write the magnitude of the vector is to write the vector's name, but put it inside little straight lines. They probably have a like legit name, but I don't know what they are. Absolute value, kind of, I guess. So we put the vector inside those straight lines, and that's another way to write the magnitude of our vector. Okay, so this idea of distance versus displacement, I kind of wanted to hit on this a little bit harder because displacement is not something that, it's not a word that you commonly hear, I suppose, unless you're like being displaced from somewhere, which is a little bit different connotation. So if I travel 5 meters to the left and then 4 meters to the right, I traveled a distance of 9 meters. 4 plus 5 is 9. So distance refers to the total distance that you have traveled. All of the paths that you take added together is your distance. Your displacement, however, is just concerned with where you started and where you ended up, the distance between those 2 points. It doesn't matter what path you took to get there. It's just concerned with the distance between where you started and where you ended up. So if you went 5 meters left and then 4 meters back to the right, you're still only 1 meter away from where you started. So your displacement is 1 meter to the left. Okay, and we have to specify that our displacement is to the left because it's a vector. The direction matters. It matters if you are 1 meter left versus 1 meter right versus 1 meter north. You'll be in a completely different place. So that's kind of the difference, excuse me, between distance and displacement. And then an interesting thing to think about is that if you go to the store or anywhere and you come back home, your displacement is 0 because there's no distance between where you started and where you ended up. So you could take the most meandering pathway that you wanted, and still your displacement is 0, which I don't know if you guys like keep track of your step counts, but you could have like a 15,000 step day and you're like, oh great, like look at me. Your displacement's still 0 if you come back home. That's kind of a bummer, but that's the difference between distance and displacement. Any questions about that idea? Okay, great. Good. We're rolling. Okay, so vector math is a little bit more complicated. It's not quite as straightforward. Lol. Remember, because vectors have a direction. Okay. Thank you, Vincent. Lol. Yes, I appreciate that. When we add vectors together, usually we'll do it graphically. And I'm going to show you, we'll go through some of the rules, and then I'm going to show you this really awesome website that will help you kind of visualize these things. So basic rules for adding vectors together or subtracting them. You can slide a vector around, but you cannot change the length of it or the direction that it's pointing, because then you've totally changed the entire vector. So you can like take it and slide it side to side, up, down, wherever you want, as long as it's the same length and the same direction. You can slide it wherever you want on your graph to help you visualize things. When we draw vectors and add them together, we add them or we draw them tip to tail. So remember, visualize an arrow in your mind. We have the tip of the arrow, which is like the point of the arrowhead. And then we have the tail of the arrow, which is down the farthest point away from the tip. And then after we've slid around all of our vectors, put them lined up with each other, tip to tail, the resultant vector, which might be a new word for you, resultant is just the result of this particular problem. The resultant vector begins at the tail of the first vector and ends at the tip of the last vector. I think that one will make a little bit more sense once you can actually see it happening in just a couple minutes. Your teacher called the tip the nose. That's funny. I mean, that's a great visual as well. Subtracting vectors is the same as adding a negative vector. So when we have a negative vector, we just take it and we flip it 180 degrees. So it's still the same length, but now it's pointing in the exact opposite direction. And then we can slide it around and do the same sorts of things with it. So right there, that bottom bullet, I have a link to a simulator vector drawing program, which we're going to take a look at right now. So I'm going to try to jump over to that thing and share my screen with you guys again. Okay, can we all see the vector addition website again? Okay, great. Looks like I'm getting the hang of this. Awesome. So this is where that link will take you. And for future reference, this phet.colorado.edu, they have a ton of really great simulations. So things like collisions and momentum and all that stuff. If you ever have questions about how to visualize certain things, this is a great resource for you. So we're gonna look at this one for vector addition, and we're gonna start off with just looking at it in one dimension first. So here we have our graph, and I'm just gonna take a vector and drop it in here. Okay, I'm gonna line the tail up at the origin or this 0 point, just for the sake of simplicity, and you can adjust this to be whatever length you want. I'm in an 11 mood kind of day. So here is our vector A, and you can see that it has that little arrow symbol over top. That means it's a vector. The magnitude of this vector, see there's our magnitude symbol. Can you guys see my mouse moving around on the screen? Yes, okay, great. So here's our magnitude symbol. The magnitude or the size, the length of this vector is 11. Whatever the units are, 11 blocks. The angle, this symbol right here is the Greek letter theta. That's typically what we'll use for angles. Although sometimes you might see other symbols But the angle of this vector is 0 because it's right there along the axis. So since it's right along the x-axis, there's no inclination up from there. So it's at an angle of 0. And let's say I want to add in this other vector b. Just drop that in right there. It's 5 blocks long. That's the magnitude. And again, it's in this this direction of 0 degrees. So thinking about our vector addition rules, if we wanted to say, what is a plus b? Well, we can slide this vector around as long as we don't change the length or the direction that it's pointing in. So I'm going to slide this vector b down so that the tail of b is lined up with the tip of a. And it gets pretty easy then to see what the total length of this would be. Our resultant vector, here it's called the sum. And I drew it right on top. So let me see if I can slide it up. The sum vector, or the resultant vector, is just the lengths of those added together. So remember, A had a magnitude of 11, B had a magnitude of 5. So the magnitude of our resultant vector, or the sum vector, is 11 plus 5, 16. Okay. So if, let's say, we put it back the other way, so now we're subtracting our vectors, you can still slide them so that they line up tip to tail like this. Okay. But now let's say, if you think about it in terms of like actual real life events, let's say you went 11 blocks east, sorry, and then you backtracked and went 5 blocks west. Sorry, I lost my train of thought. 11 blocks east, 5 blocks west. The sum of those is really the difference between them. Okay, I'm sorry. B is 6. That's a magnitude of 6. So we had A 11, B is 6, and our sum in this case is the difference because we're subtracting these two vectors. So our sum vector has a magnitude of 5. Is that your displacement? Yes or no? What do you think? Is this sum vector your displacement? Good. Yes, yes. For those of you who are responding, yes, this resultant vector is our displacement vector. It tells us the difference, the distance between where we started and where we actually ended up. Okay. So in this case, our displacement has a magnitude of 5. What is our distance? Our total distance. Right, yes, 17. Because A has a magnitude of 11, B has a magnitude of 6. 11 plus 6 is 17. So our distance that we traveled is 17. Our displacement is only 5. Okay, so that's kind of the gist of things in one dimension. It's I would say it's fairly straightforward to visualize this type of thing because when you're dealing with just one dimension, either the two are going to directly add to each other, like we saw in the first case, or they will directly subtract, yes, pun intended, they will directly subtract from each other, like we see in this case. When we're dealing with 2 dimensions, now it's a little bit crazier. Okay. So here we have vector A, and I'm just gonna, you can move this around. You can see as I move it around, the magnitude changes as I make it longer or shorter. The direction changes as I change this angle. So I'll just pick a place right there. Okay, so this vector is 19.3 blocks long, and at a direction of 21.3 degrees. And again, that is measured up from the positive x-axis. Okay, so then if we add in a second vector, here's vector b, I'm going to line these up tip to tail so that it's a little bit easier to see what's happening. This is like if we were to add these pathways together to get our distance, we would still just add our magnitudes. So 19.3 plus 10, what would our total distance be? Good, good, 29.3, great. Yep, that's our total distance. Our displacement, though, is a little bit weird in this case. We can't just add them together to get our displacement this time because they're not in exactly the same direction. And so in this case, our sum vector, if we were to drag it over here, you see it kind of completes the triangle. Right, so our resultant, again, the tail of our resultant starts at the tail of our first vector, and the tip of it ends where we ended up. So it's kind of like if you were a bird and you could fly straight there instead of having to take a roundabout pathway. That's basically the same thing as your resultant vector or your sum vector. And in this case, it is a little bit smaller than our two distances added together. Right? Total distance was 29.3, but our displacement is 29.1. Okay. And if we move these vectors around, you can see our sum vector changes depending on the particular vectors that we are dealing with, but it always starts at the tail of our first vector and ends at the tip of our, in this case, second vector, but whichever vector is last. You can do this same process with any number of vectors that you have. So I'm going to shrink this one just a little bit. Do that. I'm going to add in a third vector. So let's say that you started out walking kind of northeast, and then you started walking northwest, and then you went straight south. Okay. Again, our total distance would be all of these individual pathways added together. So 19.3 plus 10.3 plus 10 would be our total distance. But our displacement, or our sum, is just concerned with where we started and where we ended up. It's just that straight line distance from the tail of our first vector to the tip of our last vector. So regardless of how many vectors you're dealing with, you can add them together graphically in this way. Just slide them around. Don't change the length or the angle in the problem. Just slide them around so that they meet up tip to tail like these. And then your resultant vector, or the result of your path, your problem, would start at the tail of the first and go to the tip of the last. Okay, so I know it's a very visual thing. Can you do me a favor, and in the chat, we can do this mathematically, we will get there in just a moment, but in the chat, can you just give me, like, on a scale of 1 to 5, how comfortable you feel drawing these vectors, understanding sliding them around so that they add up? Okay, okay. So it looks like for the most part we feel pretty good about this. The more you see it, the more it will make sense. So hopefully seeing this helped us understand some of those rules that we just saw in the last slide of the PowerPoint. Okay, yeah, it does definitely make more sense in one dimension than two, but we'll do a couple of examples of this together in 2 dimensions so that you can see how this whole thing works. Okay, one thing that I wanted to kind of talk about, let's just take one vector A, for example, and I'm just putting it in an arbitrary length and arbitrary direction. You can see in this simulation there are these 2 other boxes that I haven't mentioned yet, AX and AY. And these things are called the components of the vector. So components basically means like pieces of this vector. So let's imagine for a second that we had some lights, some really, really bright lights way up here at the top of the page that were shining down like spotlights onto this vector. Well, this vector would then cast a shadow down onto the x-axis. Imagine that that's the ground, right? So the light would shine down, cast a shadow on the ground. The shadow of that on the ground right here, this is called our x component because it tells us how far over in the x direction this vector actually goes, right? So we can see it, if we look at this vector, it ends up at an x coordinate of 27. So our x component of this vector is 27. That's the x coordinate of the tip. And we can kind of visualize it the same way. If we had a really, really bright light over here shining this way, it would cast a shadow onto the wall that is the same height as the vector, right? And this is called our y component because it tells us how far in the y direction our vector goes, in this case, up. Okay, so our y coordinate of this point where it's ending up is 18. So our y component of this vector is 18. And you can see in doing that, we've basically created this right triangle. Colby mentioned in the chat, Pythagoras. Yeah, we're going to use the Pythagorean theorem a lot in the next couple of days. So we can see we've created this right triangle using the components of this particular vector A. Gabriel, yes, to find the angle, we would use the arctangent, and I'll go through that in just a moment. And you can see as we change the vector itself, vector A, our components are also changing. So the less far it goes over in the x direction, the smaller our x component gets. The higher up it goes in the y direction, the higher our y component gets. Okay. So I'm going to pop back over to the PowerPoint. Give me just a moment. Okay, can we all see the PowerPoint again? Great, yeses, awesome. Okay, so I would definitely recommend that you go to that website and play around with it yourself. Drag around these vectors, see how they add together to give you the sum or the resultant vector. It's actually really fun to just mess around with it. So on your own time, take a second and check that out. It's pretty cool. Okay, so like I was just talking about the components. So when we're dealing with 2 dimensions or 3 dimensions, we break vectors down into their components. And usually, like we saw in the simulation, we'll call those the x and y components to just keep in mind our graphing mindset, right? So when we make a graph, we have the y-axis and the x-axis, and anything that's along this horizontal direction we call the x component, and anything along this vertical axis we call the y component, to just match those Cartesian coordinates. So there's one component per direction, which expresses how far it's going or how much of the vector is in that particular direction. So this is where our knowledge of trig comes in. Let me just know in the chat, how many of you have seen SOHCAHTOA before? Okay, sorry. Okay. So SOHCAHTOA, for those of you who don't know or maybe are a little bit rusty in this, SOHCAHTOA is basically just a way to remember the trig identities for these three trig functions that we'll be using most often: sine, cosine, and tangent. And what this stands for is the sine of the angle S is the opposite side over the hypotenuse of our triangle. The cosine of our angle is the adjacent side over the hypotenuse. And the tangent of our angle is the opposite side over the adjacent side, TOA. So again, this is all referring to a particular direction as our reference point. In this case, this is the angle that, that we're interested in. So I'm calling that angle theta. And here's our right triangle. The hypotenuse is the longest side of the triangle always. The adjacent side is whatever side is next to our angle, and the opposite side is whatever side is opposite from our angle. So we're going to be using these trig functions whenever we have a vector on an angle. And we want to break it down and see how far over in the x direction is this going, and how far in the y direction is this going. What are the components of this vector? So we're going to be using these trig identities, those particular ones, pretty frequently. When we're expressing the components, there are a variety of different ways that we can do that. And I have a bunch of them here on the slide. This isn't all of the ways that you might see, but it is, I would say, the most common ones. So this first example here, you might see this in your math class, like your x coordinate and your y coordinate. So this tells us our x component and our y component of a particular vector. In this case, our units are meters per second. So we're dealing with a velocity, how fast we're going in a certain direction. Okay. You might also see it written like this, where the top of the bracket is the x component and the bottom is the y. You'll notice there's not a division line in this bracket because it's not division. It's something called a matrix format. I'm not going to use this particular method in this class, but I just wanted you to be introduced to it. Okay. You might also see them written in terms of I and J and K if we're dealing with 3 dimensions, but they basically mean the same thing as X and Y and Z in our Cartesian coordinates. You might see them written as X hat and Y hat to show you that it's this far in the X direction and this far in the Y direction. Usually I will write it in like this: velocity in the X direction is this, and velocity in the Y direction is this. I think that just makes it really straightforward. So that's usually going to be my preference. You may also see it written like this: the magnitude at an angle counterclockwise from east. So you'll notice that this 19 meters per second seems like it came out of nowhere. It doesn't match the negative 4.92 or the 18.4. It just kind of magically appeared. And that's actually the magnitude of this vector. That would be the length of our sum vector if we added them together graphically. And there is a mathematical formula that you can use to help you see that. So each of these is useful in a different context, but those three that I notated are going to be the most common ones that you'll see in this class. So when we add vectors that are on angles, we add them together based on their components. So we break all of our vectors down into their x components and their y components, and then we just add those together. So we add all of the x's together and all of the y's together. So in this case, if we have one vector, vector A, that has an x component of 3 and a y component of 9, plus vector B that has an x component of 2 and a y component of -5, we can add those x's together. So 3 plus 2 is 5. Add the y's together. 9 plus -5 is 4. And this would tell you the components of our resultant vector. The x component is 5, the y component is 4. If we wanted to know the magnitude of the resultant vector, or that sum vector, we would use the Pythagorean theorem. You might see it as a squared plus b squared equals c squared. We've just rearranged that to get the variables that we're actually interested in. So our magnitude squared is the hypotenuse of our triangle. Well, it's c squared in that equation. So the magnitude is the square root of our x component squared plus our y component squared. So 5 squared plus 4 squared, take the square root. And that gives you a magnitude of 6.4, whatever our units are. To find the direction that it's in, we take the inverse tangent of y over x. And that would give us an angle of 38.7 degrees. Okay, so these things work no matter how many vectors you have. If you have 3 vectors or 4 vectors or 5 vectors, the same rules hold. You add together all of the x components, add together all of the y components separately, and that will give you their components of those that resultant vector. If it's in 3 dimensions, you would adjust this equation a little bit and do the square root of x squared plus y squared plus z squared. For some reason, I lost my chat window. I don't know exactly where it went, and I can't seem to get it back. So if you have a question, please feel free to unmute yourself momentarily and just like get my attention and ask. I'll keep trying to figure out where my chat window went, but I can't find it right now. Okay.
Then why don't you hit the chat on the bottom of your screen?
So my screen looks a little bit different than yours because I'm hosting this.
I know I've hosted a Zoom meeting before, for a couple times.
Okay.
But
I'm sorry.
on the Zoom, I had a couple times before he died without any warning on April 30th.
Okay, let me pause my screen sharing for just a second and see if I can get it back. Sorry for the momentary interruption.
You don't need to be sorry.
Thank you.
Welcome.
All right, let me try this again. All right, well, I'm still not seeing it. So we'll just keep rolling. And again, if you have questions, I'll try to periodically open up my chat if I can. Okay, great. So when we are multiplying vectors together, which does happen sometimes, if we're multiplying a vector by a scalar number, then we just multiply each component by that particular scalar. So let's say we have vector A, and it has 3 dimensions, ooh, x, y, and z. So our x component is 3, our y component is 4, and our z component, which would be like out of the screen, like towards you or behind you. We just multiply each of those components by that scalar number. So A is 3, 4, 5. 2A is 2 times 3, 4, 5, or 2 times 3, 2 times 4, 2 times 5, which gives us 6, 8, 10. Okay. We just distribute that, that scalar into each of the components and multiply. If we're multiplying a vector by a vector, though, whoa there. We'll get to that in a little bit once it's relevant. I prefer to do that in context. Those are called cross and dot products. There are 2 different methods to do that depending on the particular scenario. So we won't focus on that today, but we will get there in a little bit once it's relevant in context. So that is sections 1.9 and 1.10 in the book, and we're not quite ready for that yet. Okay. So I want to do a couple of examples together. I have 2 examples that will kind of wrap up the class with. So example 1, this comes from the textbook, example 1.5 in the textbook. A cross-country skier skis 1 kilometer north and then 2 kilometers east on a horizontal snowfield. So we're not dealing with 3 dimensions, just 2 dimensions. How far and in what direction is she from the starting point? So if we think through our problem-solving strategy that I talked about yesterday, remember it's called IC. The I is identify. So we want to identify what's important in this particular scenario. Identify our target variable that we're looking for as well. So we're looking for 2 things. We're looking for how far she is from her starting point. Is that distance or is that displacement? That is our displacement, the distance from the starting point to where she ends up. That's our displacement. And a good clue for that as well is that it asks, and in what direction? Distances don't really care about the direction. Displacement does. Right, so how far and in what direction is she from the starting point? That's our displacement vector that we're looking for. So next up, we set up the problem, and I definitely recommend, especially when we're dealing with things like vectors, that you draw the scenario as best as you can to scale. So here's the picture of what that looks like. She goes 1 kilometer north and then 2 kilometers east. And our resultant displacement, or the result of that, is what we're looking for. So you can see in this example, it's a pretty simple right triangle, conveniently. So what we would need to do is use the Pythagorean theorem to figure out how long that particular length of the triangle is. So to do that, again, we take our 2 component values, square them, and add them together. So our x squared is 2 squared. Our y value is 1 squared. When we take the square root of that, we get 2.24 kilometers. That's our magnitude of the resultant. The direction that it's pointing in is that inverse tangent equation. And the reason why it's an inverse tangent is because of those trig identities. Keep in mind SOHCAHTOA. So TOA, the tangent of our angle. In this case, it's phi, but it's just another symbol for angle. Tangent is opposite over adjacent, which means that if we want to isolate the angle by itself, we have to take the inverse tangent of opposite over adjacent. And that gives us this 63.4 degree angle. It's also called arctan. Yes, I see that in the chat. Arctan and inverse tangent are the same thing. Okay. Any questions about this example? How did I get 2.24? You got 5. Did you take the square root of your answer? Because remember, the magnitude is the square root of 1 squared plus 2 squared. Your calculator wasn't on degree mode. Oh, I'm so glad and sorry, but so glad that that happened to you, because that is a really common problem. A lot of people will leave their calculators in radians because of math class or something like that. And so you get your answer in radians instead of degrees. I mean, it's fine if you, for me, it's fine if you leave it in radians. I would say for problems such as this, the better one would be degrees. So double check your calculator to make sure that it's in degree mode. Does FIT let you use graphic calculators in physics and math? Yes, physics, math, it depends. I've had some math classes where you weren't allowed to use any kind of calculator at all. Things like calculus and differential equations, where you're more manipulating equations than like solving a problem. So yeah, it just depends on the class that you take. Okay, any other questions about this example? We're gonna do another one real quick. Okay. All right. Example 2. After being left at home alone, Kevin McAllister realizes he needs a new toothbrush. To get to the store, he walks 9 blocks west and 3 blocks north. Each block is 1/8 of a mile. After which he must take a 0.35 mile shortcut northeast through a park to avoid capture by the police. Long story. How far is he from home now, and in what direction should he walk to get back to his house as quickly as possible? Side note, this is one of my favorite Christmas movies. I watch it every year. End side note. So we want to identify our target variable. And in this case, we're again looking for how far he is from his starting point from home and which direction that is where he ended up. So we're again looking for a displacement vector. To set up the problem, we're again going to draw a picture. So this little black thing is his house. Okay. So Kevin walks 9 blocks west and then 3 blocks north to the store. And then he walks runs more, 0.35 miles northeast through the park. And we want to know how far he is away from home and what direction he needs to walk. So this is kind of our our setup. Do you guys notice anything problematic about this problem before we just jump in and start calculating things? I'm seeing a lot of good thoughts in the chat. Yeah, so there are a couple of things. First of all, you notice that it's not a nice, simple triangle. We can make it into one though, and I'll show you how to do that in just a moment. But yeah, I would say the first problem is that we're dealing with mixed units, blocks and miles. And we don't want to mix our units like that. That's kind of a problem. So we're going to need to convert our units of blocks into miles. But we know that each block is 1/8 of a mile. Okay, so it's not too difficult to do that. 9 blocks becomes 9/8 miles, which is 1.125 miles. And 3 blocks becomes 3/8 of a mile, which is 0.375 miles. So now all of our units are consistent and we are good to move on to the next step. Okay. Also, we know that this angle, we know that he's going northeast. So we're going to assume that he's going directly northeast, which means that that angle right there is a 45-degree angle, because 45 is half of 90. So directly northeast would be a 45-degree angle. Okay. Okay, can you guys all see my example again? Sorry, technology is struggling. Okay. So just taking these equations from the previous slide, our magnitude of our vector is the square root of x component squared plus y component squared, and the direction is the inverse tangent of the y component over the x component. Now, that's great when you have a triangle, but as several of you pointed out, we don't have a triangle. So let's make one. Right? We can break down our picture into this like giant right triangle. Okay, and the hypotenuse of the triangle is our displacement vector, how far he is away from home. So if we just drop like a straight vertical line down onto the x-axis and then go across the x-axis from there, we've just created this giant right triangle. So we can't plug numbers into our magnitude equation until we know how big the sides of that triangle actually are. So we need to figure out how to get the components, the x and y components of that orange triangle. Now we know that he walked 9 blocks west and then kind of ended up backtracking a little bit to the east when he cut through the park. So we see there's our 9 blocks west, but then he backtracked a little bit in the park. So if we take our 9 blocks west and add on, kind of weirdly add, but add on the x component of that smaller triangle up top, then we get, you know, our actual length of that bottom orange line. And similarly with the y component of that orange triangle, if we take how far north he went to the store plus how far north he went through the park, then we end up with our y component of the orange triangle. Okay, so in order to find those components of that shortcut through the park, we have to remember SOHCAHTOA. We know the hypotenuse of that triangle is 0.35 miles. So we're going to use sine to find the opposite side, the y, the green component, and the cosine to find the adjacent side, or the x, the red component. So think about SOHCAHTOA. Cosine is adjacent over hypotenuse. We want to know the adjacent side length, so we'll rearrange that equation. The adjacent side is hypotenuse times the cosine of our angle. And we would do a similar sort of rearrangement for the sine to get the opposite side. So when we think about adding vectors together, we're going to keep in mind that typically anything up or right, north or east, is positive. Oops, sorry. Oh, and anything down or left, south or west, we're going to call a negative, just so we kind of keep those directions in mind. So the x component of our shortcut triangle is right there for you in red, 0.35 times the cosine of our angle 45. Which means when we add these two vectors together, since we're starting off with that 9 blocks west, west is a negative direction. So that's negative 1.125 miles. And then we go back east, which is a positive direction. So we add 0.35 times the cosine of 45. And that gives us a negative 0.8775 miles. We do something similar in the y component. And you can see that shortcut through the park portion is in green in that equation. So we have the y component of that bottom length, 0.375 miles, plus this y component from the shortcut, gives us the total y component, which is 0.6225 miles. So the magnitude of our displacement vector then is this x component squared, so our negative 0.8775 miles squared, plus our y component squared, 0.6225 miles squared. When we take the square root of that, it gives us 1.076 miles is our displacement. And to find the angle, we take the inverse tangent of y over x, and we get negative 35.35 degrees. We have to be careful just taking that angle at face value, because that's actually referring to this angle. Negative 35 means down from the x-axis. If we were asked to find the angle with respect to home, so this angle, again, we measure all of our angles from the positive x-axis. So if we were asked to find the angle with respect to home, we would have to add 180 degrees to our answer. And that's just because when you take the inverse tangent of something, there are two numbers that would give you the same inverse tangent answer. And your calculator can only give you one of them. So this is why it's so important for you to draw a picture of what is happening so that you know which angle it is that you're looking for. Are you looking for this angle with respect to where you ended up and are now trying to get home? Or are you dealing with the angle with respect to home? It makes a big difference and will give you a different answer. Okay. Let me take a look at this chat real quick. So Colby, when you say what direction do you mean the counterclockwise angle from the positive x-axis? Woohoo! Yeah, so that ties into what exactly we're looking for, and kind of that issue that I just addressed. Can you use Pythagorean theorem and SOHCAHTOA on a non-right triangle? Um, I I would say the best case scenario is to force it to be a right triangle, um, and then it's just easier to visualize that way. If the angle is 45, we can assume that both sides measure the same. Yes. Okay. Does that answer your question about this exam? I know it's a lot to look at on this screen, but do you guys have any questions about this example? This example ties together quite a few of the topics that we talked about today. Breaking vectors down into their components, adding together more than two vectors to create this crazy shaped problem. Graphically adding vectors together, you add them together tip to tail, and then your displacement or your resultant vector kind of completes that shape, whether or not it's a triangle. Okay, it's looking like there are no questions coming in. So I'm going to call it here for today. We had just a couple of minutes left, 2 minutes left. So we're going to start here tomorrow. We have a little bit more to talk about concerning vectors before we jump into chapter 2. So we'll finish up chapter 1 tomorrow, and then we will go ahead with chapter 2. And I'm going to show you this slide. Okay, so do you guys see this slide that's called bonus activities? Give them a try. Yes. Okay, good. So you'll see this again when we actually finish chapter 1. We're not quite there yet, like I said. But these are going to be a couple of resources for you to just get some practice with drawing vectors or calculating components, that sort of thing. I recommend that you pick at least one of them and give it a try, depending on which thing you feel like you need the most practice for. So this first activity, Vectors, The Adventures of Shelley the Sea Turtle, that will give you practice drawing vectors with the particular length and direction. You will need a ruler and a protractor and a big piece of paper to do that activity, but it will help give you practice drawing them if that's what you need. If you want more practice using those trig identities, sine, cosine, tangent, and breaking down vectors into their components, check out trig practice. And then if you want practice with kind of all of these concepts, I posted a picture of the problems from the textbook, sections 1.7 and 1.8, to just start working your way through and see how you do. For all of these things, I'm going to be posting the answer keys on Friday, not worked out solutions, but I'll be posting answer keys so you can check your answers. I recommend that you give one of these or several of these a try. Okay, so we are done for today. We'll meet back at 3 tomorrow, and we'll pick up where we stopped today. If you have any questions, feel free to stick around for a couple of minutes. I'll be here. You can type them, you can talk to me, but I will see you all tomorrow. Have a great one.